Hey, you 13s, how's it going, guys? I'm sorry if a couple of people got confused. I scheduled like 3 webinars this morning, and I think a lot of people have ended up in the wrong place, which is quite entertaining, really. I'm sorry if a couple it's kind of my fault. Funny. Got Jasmine. We're doing well on the register. Jasmine, Emma, Nikita, Dana. Although I feel like we're usually doing better. There's Tenzi and Kayun. We're getting there now, you see, folks. We're getting there. We're getting there. Oh, right. Missing quite a few people. Missing Dat, Ria, Ben, Ivan, Mika. Oh, actually, that's all. That's not as bad as I thought. There's Dat and Ivan. Amazing. See, we're slowly getting there. There's Dat. And there's Ivan. Mika, Ben, and Ria now. There's Ria. We're doing well now. We're only 1 minute in. See if we can do it in under 2. Ben and Mika to go. Just Ben and Mika. Right, guys. So we're going to be working through. There's Mika. Amazing. We're nearly there. Just Ben to go. Now, Ben does tend to be late. So I'm thinking that I should just crack on at this point. Yeah, why not? I'll assume Ben's going to be late. I'll mark him as absent for now, and then I'll get back to him when he arrives. Okie dokie. Save. Right. Okay, guys. So today we're going to continue with our equilibrium topic, which is nice. Last lesson we did a bit of AS review. I didn't set you guys a homework. Thought I'd give you a break since you've been having so much from me anyway. You will get homeworks every lesson, pretty much. The next one's going to be on KC. So our learning objectives today, folks, which are not there, which are here. There we go. So 3 learning objectives today on KC, on equilibria. So number 1 is be able to write KC equations. I shouldn't do that. It's the wrong word. I'm going to change it. Expressions. Yeah, but we don't like the word equation now because equation suggests like a chemical equation, but this is an expression, which is what's used in mathematics. Yeah, so something like A is equal to B plus C. Is that if you've got an equal sign in it, technically it's an expression, not an equation. Just throwing that out there. But we're going to be writing KC expressions, give units of KC. And we need to have this fact. And this one here, guys, I need you to put in like a little sparkly bubble. This one's really important. The only thing that affects KC is temperature. Mr. Duncan, we can't see your screen. We can see your hair. Oh, my bad. Go. Well, don't I feel sheepish? Thanks very much, guys. There we go. 3 learning objectives. I'll give you a minute just to write those down. Only temperature affects KC. That is so important, guys. That needs to be locked down in your understanding. Yeah, absolutely clear as day. Nothing else does. I will actually talk to you about this because there is a clause in here. Yeah, but that still stands. I'm not saying that that's wrong. It's not. The only thing that affects KC is temperature. Yeah. And I will explain that to you when we get down to it. So last lesson, we looked at how K evolved. I love the fact that it evolved into KC. And the C stands for Chatelier. Yeah, for equilibrium, because he's the top dog for equilibrium. Yeah, and we started the process of understanding what a KC equation is. And the great thing is that it's nice to do that kind of evolution and to explain where it comes from. But in reality, I just really want to get you guys into a really good habit of being able to write them. I'm going to put a couple of nota benes in here all over the place. But question number 1, we're going to do K. Oh, blimey, that's too thick. Let's try that again. All right. KC expressions. KC expressions. Okay, so, and this is not complicated, guys. The note is number 1, products. Products over reactants. I'll explain that to you as well in a second. Products over reactants. Number one, this is so important. Yeah, this is deemed the most important factor. Number one. Yeah, products over reactants. I will explain that to you in a second. The next thing is that they do have powers, but the powers are now no longer orders. They're now the stoichiometric ratios. Yeah. Reagents. Shouldn't do that. Species in equations, in expression are to the power in the balanced equation. That doesn't make any sense. Species in the expression are to the power of their stoichiometric ratio, of their stoichiometric, I can't spell it. Oh no, stoichiometric, stoichiometric, I don't think that's spelled right, someone check me. Stoichiometric ratio. If anybody's going, I don't know what stoichiometric ratio is. Yeah, this is balanced numbers. Balanced numbers. Yeah, I'll explain this. By the way, it'll all make more sense once you actually see it in the actual examples. And that basically sums it up. So the question is, so hang on a sec. There's something odd here. Because this is where the nota bene comes in. First nota bene. So why not orders? Why not orders? Stoichiometry, the O and the I switch round. Did I get that right? No! So close. So close. Stoichiometric. So the O and the I is switched. Wow. Thanks, Dad. I really appreciate the fact that you're like on it. So the O and the I are backwards. There you go. Stoichiometric ratio. Yeah. Stoichiometry, the study of balancing equations. Why not orders? Yeah. The reason why is what we're saying is that if we compare a rate equation, yeah, which is only reactants. Yeah, I'm just going to give you an example. And we know that these here are orders. Now, the orders are the power numbers that tell us how A and B correspond with the rate. Yeah, these values, this is where I need to be able to do this in my notes. These values correspond to the effect that A and B have on the rate. Now, in equilibrium, that no longer applies. It no longer applies. Kc equals products to their stoichies over the reactants to their stoichies. I love that. Yeah. So the reason why this doesn't matter is because this is at equilibrium when the rates are the same. So if the rate is now constant, it means that we don't look at how they're going to affect the rate of that reaction, because this is at a constant rate. Yeah, constant rate. You can't have a Kc value if you haven't reached equilibrium. Constant rates, yeah, brackets, at equilibrium. Yeah, I hope that makes sense. Does that make sense, guys? Yeah, the Kc no longer needs the orders because we are measuring this at the point where the rates are equal. Yeah, which means there's no fluctuation, there's no change. So therefore, their impact on Kc will only be at the point where the rates are the same. So you don't need to ever worry about their orders. But the values in the balanced equation will impact that makes sense. Good, thanks, Ben. Oh, Ben suddenly arrived. Thanks, Ben, for telling me. Right, good. I'm glad that makes sense. Okay, so let's now put this into practice because it's really easy. Super, super duper easy. Yeah. So question number 1, I'm going to do the good old Haber. We love the Haber. We love the Haber. We love the Haber. I've gone mad. I'm balancing whilst I'm writing. Stupid, Mr. Duncan. Stupid. There we go. There's another point here to... Oh, yeah, go on. Oh, sorry. But then don't you revise KC from the rate equation? Derive. Yes, of course you do. But their orders will no longer apply because KC is at the point where the rates are equal. So that you're not looking at... Remember that this equation, a rate equation, is saying... This literally translates to, how do these guys affect this? That's not what KC is. KC is saying... Right, by the way, I haven't actually written this down yet. Suddenly realized there's something really important that I've missed. Guys, so hang on. Hang on. Okay, let's first of all, guys, I'm going to come back to you in a sec, Dat. Can we first of all translate this, please? Question. KC expression. Right, can everyone pause the video and have a go at translating this? Wow, I don't know why I went supersonic then. This into a KC, please. And remember, products over reactants. People often ask me, why is it products over reactants? Because, and I'll tell you that in a sec. Right, so this is super easy. Got loads of nota benes going to be appearing everywhere, guys. Yeah. Right, KC equals products to their stoichiometric ratio. Let's color code this. Yeah, that's what stoichiometric ratio is. Nitrogen to the power of 1 times by hydrogen to the power of 3. Let's color code it. Color code it. Yeah, there we go. It's nice to see it. And of course, that's a 1 and that's a 1. There we go. Nice. So there's our KC expression. This is nice and easy, isn't it? You just translate it out. So here's the next nota bene. So at this point, students often say, so what's the point of KC? Yeah, question. And this is a nota bene, really. It's a nota bene question. Ooh, nota bene. Yeah. What is the point of KC? Right, guys, and I love this. So the answer, which I'm going to put in green, answer, KC is a numerical value that represents the, ooh, that's weird. It was coming up with little lines. Oh, God. Don't want to see an error like that on my laptop. KC is a numerical that represents the position of equilibrium. This is super important. So what does that mean? Now, this also follows up with why is it products over reactants? So whenever we get an equilibrium, yeah, A plus B goes to gold. Yeah, and everyone knows we love gold. Gold is worth money. Everything in chemistry is about products. This makes me money. Yeah. Now, if I ever come up with an equilibrium like this, and I go to a company and say, right, guys, I've just discovered this amazing reaction that turns A and B into gold, but it's in equilibrium. The first question that I'm going to be asked is, what's the value of KC? So here's the next really important nota bene. Loads of nota benes, guys, and these need to be accounted to memory. Next nota bene. A KC is linked to products. That's why it's products over reactants. Yeah. Is linked to products. Notice my capitalization here, folks. The bigger KC, the more product. Yeah, the more product. Yeah, it tells us the position of equilibrium. Yeah, so if I have a KC of value 58, I'm going, woo, yeah, boom, that's what I like to hear. Woo! Yeah, because that's telling me that the equilibrium is lying heavily towards the gold side. Yeah, lots of gold. The reaction is lying that way. There's more gold than AB. This is good. But if I get a small KC, if I get KC of 0.00025, I'm like, boo, this is bad. Yeah, because what that's telling me is that the equilibrium is lying massively towards that side. Yeah, you can never have a negative KC, by the way. It's always nice to know that. That's another nota bene. Nota bene's all over the place, guys. KC is a numerical value that represents the position of equilibrium. It's a value. Yeah, it allows me to actually know where it lies. Does it lie to the left or does it lie to the right? And you can get some extraordinarily low KC values. I've seen a KC value as low as 10 to the minus 12. Yeah, what that means is the reaction's deemed pretty much not happening. Yeah, I've seen that question asked. Oh, it was done. It was done. Yeah, I can show you it. I can't actually show you it on the paper. I know it. Yeah, question. This is an exam question now, folks. This is an exam question example. Exam question. Ethanoic acid. Ethanoic acid follows this equation. Follows this equation. With a KC slash Ka, they're actually the same thing. This is an equilibrium constant for acids. With a KC of oh no, hang on a sec. I know this. 1.7 times 10 to the minus 5. HCl follows this equation. With a Kc slash Ka, the equilibrium constants for acids, of 6.23 times 10 to the 23, I believe, or 28. I mean, actually, it's massive, 10 to the 20, something like that. What does this suggest about the equation and what correction should be made? It was a horrible question. It was all wordy, and it would suggest, yeah. Suggest what is wrong in equation. And what you had to say was Kc in red, Kc for HCl is so large, it's massive, so large, the reaction lies hugely to the right, products, left to the right, to the right, hugely to the right. So not deemed reversible. This is where I have to say one of these awful sentences, by the way, which I actually despise in myself. I remember getting this when I was at school in my lesson, and they said, all reactions are in fact equilibriums. By the way, I totally call on that one. Like, that is, it's not true. I hate that. Chemists say it to mess with kids. Yeah, and it's not a good thing to say. It is not true. We do not deem every reaction to be reversible at all. It's garbage. Don't ever let anyone tell you otherwise. Yeah. If you combust paper, you ain't not turning that back into paper. It's just rubbish. I do hate them when they do that. Yeah. It's one of those stupid mathematical things that they feel like they're allowed to say and they shouldn't do. I totally disagree with it. I hope, but does that make sense, folks? And this strengthens the concept of understanding what this value means. It's telling us the position of equilibrium. Yeah. So this one here, this one here is tiny. Yeah. This is small, meaning it lies in this direction, lies to the left. This one is enormous. Therefore, it lies heavily in this direction. Good. I'm glad that makes a bit more sense. Putting it into an exam style question like that, which, by the way, that was 3 marks and most students came out with nothing. Loads of students were just like, I didn't even know what to do with it. Yeah, I didn't even know what the values really meant. I didn't really understand that I needed to mention it was deemed to the right, and then why was it needed? They didn't even understand that this really confused them. That foxed them entirely. It was a mess of a question, really, really hard. I remember that one very well, because the kids came out saying, sir, there was HCl and equilibrium, and I went, what? Are you having a laugh? And they were like, no, they asked us about the KC value for it, and I was like, oh, that's bad news. Because I knew what they'd done, and I hadn't really spent enough time talking about those kind of things with them. I'd give them all this. Some of them did get it, but it was a tough 3 marker that. So, not complicated, not difficult. Let's have another go at being able to give another couple of KC values. A couple of KC expressions. Question number 2. Yeah, let's go for... this is where you see I start messing with you and giving you silly equations. But I want to give you real ones in this case because it's useful for me to reinforce your useful ones. Yeah, there we go. This is a great one. Comes up a lot at A-level. Yeah, I'm hoping you're going to make another realization in a minute, guys. The state symbols matter. Right, there we go. So, guys, can you now convert my equation into a KC expression? Yeah, convert that into KC, please. Express. Choo-choo, it's the KC Express. Shouldn't it? oh, you see what I did there? Like, the word, I'm going to stop. Oh, no, I'm so sorry. Oh, such a dad joke. Right. Go, go, go. Right, you guys are probably finished by now. KC equals products over reactants to their stoichiometric powers. Yeah, over SO2. How easy is this? What a lovely game this is. But that's to the power of a half. Power of a half. That's correct. It is true. It can't be done. Can't be done. Sorry, I've lost it. Lockdown. That's all I've got. Did everyone get it? Give me a thumbs up, guys, on the chat if you got it. Booyah! I've got to do all the bloody maths games in a minute as well. Right. Yeah. Everyone got that? Give me some feedback, please, on chat. Nice one, Nikita / Natasha. I just got Donna just gave me a smiley face. Jasmine, yup. Ria, yup. Ivan, yup. Amazing. Love it. Kayun, yup. Fab. Excellent. Okay. So I'm going to give you another one. I'm trying to give you one that foxed people in the past. I'm trying to give you real ones as well. This is my problem. And my brain's not fully working yet today. I'm trying to think of all the... Oh, equilibriums, of course. Yeah, ethene. Yeah. There we go. Ethene plus steam. Yeah, gas equilibrium to ethanol. Gotta love ethanol. There we go. And that's a gas as well. Nota bene at this point. Gonna add a nota bene to this, folks. Only gases can appear in Kc. Yeah, only gases can appear in Kc. Is that correct? Certainly is in Kp. Yeah, I'm pretty sure that's correct. The reason being is, yeah, I'm pretty sure that's correct. I'm trying to think of examples where that might be, and I'm pretty sure that's okay. Kc deals with gases, and Kp does as well. Coming to Kp in a bit. I'm going to do Kc this time, then Kp next time. So, equilibrium, Kc expression, Kc express, choo-choo. I'm sorry, damn it. Ugh. We've got concentration, CH3, CH2OH, ethanol to the power of 1 over ethene, and steam. Yay. There we go. We're done. 1 to 1 to 1 to 1 to 1. How easy is that? So nice and easy. So we can now write Kc expressions. But what about the dissociation of HCl? We used Kc, but they weren't gases. Yes, you're absolutely right. They were all solutions in that situation. Yeah. In reality, yeah, they're separated. They're all. Yeah, I realize that. They're all in aqueous, of course, aren't they? That's in reality what they are. They're all in an aqueous environment. In reality, you don't. This is why I gave this, Ria. That's a good point. I'm glad you mentioned it. It's why I gave Ka. Ka is the acid dissociation constant, which is an equilibrium in itself. Ka is literally the acid version of Kc. And that's why you give Ka, because they're all in an aqueous environment. That's why. Good question, though. It's a good point. You can give Kc values, but you can't really play around with Kc as an expression without them being gases. I'm going to have to track down a question. Yeah, sorry about that. I hope that clears things up. I'll find some questions where they actually give you equilibriums where some of them. So, by the way, the examples are when you have Okay, hang on a sec. I've got one. So, guys, in here, of course, if you start including catalysts, yeah, the catalyst won't appear in the Kc expression. Yeah, they just don't. They're not reagents, they're not products, they're not there. Remember that the equilibrium, it's because of the fact that only temperature changes it. I probably ought to drop into that at this point. Okay, so I just want to quickly go to my learning objectives. It's definitely worthwhile me going through these. Write Kc expressions, I think everyone can do that. Right, okay, give the units of Kc. Let's run Kc units, because I think you guys are always going to be on this one, because it's an extension of K again. Yeah, so we can put a little subheading, please, of Kc units. So Kc units, not complicated, exactly the same thing as K. Yeah, we can create a Kc expression. Yeah, and what we realize is that the brackets means concentration. Yeah, we know, nota bene, just a reminder, nota bene, square brackets means concentration. Yeah, and what that means is that if we've got this equilibrium, nitrogen plus hydrogen, let's go back to the Haber, goes to ammonia, balance it. Ooh, I made a mess of that. Balance it. Right, and I create the expression concentration of ammonia to the power 2, nitrogen 1, hydrogen 3. We realize that this is just the same as Kc. Sorry, for the previous question with SO2, if you multiply the ratios by 2, it becomes a 2 to 1 to 2. You'd get a different Kc value, right? Yes, you would, Kayun. I'm coming to that. Factors that affect Kc. I'm coming to it. By the way, well done. I'm very impressed. It's all maths game. That's why I said before, I've got to teach you guys the maths games. But yes, you will get a different Kc value if you balance the equation differently. Yes. Right, so Kc units, and you guys know what I'm going to do here, equals moles per dm cubed over moles per dm cubed. I'm going to color code these. Yeah, that's the red one because it's top. This is the blue one. Yeah, and then the yellow one. And there's 3 of them in this case. Moles per dm cubed. Moles per dm cubed. I know you mathematicians are literally squirming as I do this right now. It's just the way I did it because I've found myself making fewer mistakes. Yeah, this one here is this guy because it's to the power of 3. So I give it, oh, I've missed one, made a mistake, haven't I? Thank you. That's why I do it. Yeah, moles per dm cubed on the top one as well. There's 2 of them. I made an error. I wonder how many people spotted it. Did anyone spot it? No, not off the bat. Oh, moles per dm cubed, because that's to the power of 2. I'll get rid of that and just 2. You can kind of see what I'm trying to do here, folks. Yeah, right, now cancel out what cancels. I'll cancel with green. He cancels with him. He cancels with him. 2 left on the bottom. Right, bring it up. 1 over. Yeah, we're going to do the reciprocal. So the units for this KC units are going to be moles to the -2, because these get combined. Yeah, if you combine that, it's moles to the power 2. And this would be dm to the -6, but I'm going to take the reciprocal, so I flip it. There we go. So there's my units. Not difficult, guys. Yeah, not difficult. It's the same as the KC trick. Yeah, so I feel like I don't want to spend a huge amount of time doing this, but I'm going to ask you guys a question. I'm going to ask the one that tripped up a couple of my kids. Yeah, so question number 2, going back to this guy. Yeah. This is all because of Kayun's bit. Right, guys, can you please, number 1, give me the KC expression, and number 2, give me its units. Off you go. Pause the video now and continue when you have your answer. I feel like I could totally do like an over voice. It's like my proper elevator voice, that. So the KC expression becomes KC equals, can I just mention, really bad habit that students seem to pick up without me doing, which is they just write down this. Yeah, they just write down this bit. You can't do that. You have to write down KC equals. You can't miss that, guys. You just can't. Yeah, to the power of 1 over SO2 to the power of 1 and oxygen to the power of 1/2. Right. What are my units? Cancels, cancels. I'm actually going to do it in its entirety. Yeah. So therefore, units become KC equals moles to the -3, moles per dm cubed, over moles per dm cubed, and this is the clever one, moles to the 1/2 dm to the 1.5. I've just halved the units, the unit powers. This cancels with this one, flip it up. Yeah, final answer, moles to the -1/2 dm, that should have been minus, and this is to the 1.5. There we go. Those are its units. Moles to the -1/2 dm to the 1.5. And that is correct. Weird or what? That question came up a couple of years back and I hadn't taught it, and some of them freaked out. It's all maths, this, guys. I'm not going to lie. Knowing how when you put things to, like, when you put orders to an order, what happens to the order? Yeah, because what they're doing is we realize that this is moles to the -1 dm to the -3 to the power of 1/2. Yeah, well, what that means is if you're multiplying powers, you're just then multiplying by, you're just multiplying it as you'd expect. 3 times 1/2 is 1.5. It's the same as dividing it by 2. Yeah, it's the same thing. Multiply by 1/2 is the same as divide by 2. So it's just maths games, this, guys. It's all to do with powers. Yeah, and I got into teaching this because when I first started teaching, I thought that the maths teachers would be doing this all for me. So I made an assumption that all the kids knew it. And then I rapidly realized that they really didn't. And it does need to be put into a chemistry context. It does need to be retaught. How teachers evolve. Cool. By the way, can I give a shout out on the video, please? Did everyone get my expression? Give me a number 1, 2, or 0. If you got both right, give me a 2. If you got 1 right, give me a 1. If you got none right, give me a 0. Let me know. It'd be nice just to see some numbers on the chat, please. Bit of feedback. Go on, guys. Go, go, go. Go, go, go. Donna, thank you. Donna put, yup. Oh, hang on. 2. Nice one, Donna. Jasmine, 2. Tenzi, 2. Ivan, 2. Nikita, 2. Dat, 2. Amazing. You guys know what you're doing. That's awesome. Yeah, fab. Really impressed with that. So that means that you guys understood this before my kids in my other school did, which is amazing. Really proud of that. That's great. Thank you. Really nice to see it. Look at that. Great feedback on the classroom. Got a nice 9 out of 11 people there giving me that. It was amazing. Thanks, guys. Appreciate it. That's fab. Look at that. 2, 2, 2, 2, 2, 2, 2, 2, 2. That's outstanding progress. Loving it. I'm loving it. Right. The next thing is, right. Can we do factors affecting factors affecting KC? Boom. And I'm going to put onto the chat, what factor affects KC? It's in my learning objectives, you see. It's in my learning objectives. So now this for me is really important because everything in exams is a trap. And they walk you into them. Thank you, Dana. Spot on. And that is the only thing. Apart from, it's the only actual factor in terms of possible changes. The balancing equation changes it too, which I'm going to come to now. But when I say factors, yeah, what I'm actually talking about is all the temperature, pressure, concentration, all that jazz. Yeah. So, and this is just going to come across as facts. Number 1. Only temperature, temp affects KC. I'm just going to then write underneath it in black, yeah? What this means is, therefore, pressure, no. But isn't the coefficients of KC equation supposed to buy in the realms if natural numbers so that it is standardized and comparable to other KC values? Oh, dat. Think about it practically. Yeah, because you guys have been taught for years. Dat has come up with a very good point. Yeah, you guys have been taught forever that you can give multiple balances. Yeah, SO2 reacts with O2 to give SO3, and you can balance it like this. Yeah, and then this one, SO2 to the half of O2 goes to SO3. Yeah, and you guys get told that these two here are the same. Yeah, and to some extent, they are. The ratio is actually the same because if you do it to a 2-to-1 ratio, the KC calculated would be the square of the KC value of the previous one calculated. Well done, Dan. He's already got the maths tricks, squaring it. Absolutely right, Dat. So, in fact, hang on a minute. If this isn't really the same, in terms of equilibrium, these two aren't the same. Yeah, there's a clause in here. Yeah, for equilibrium, the ratios represent how you set up. Yeah, the ratios represent how you set up the initial closed system. If I set up a closed system, 2 closed systems, in this one, I'm going to add 2 moles of SO2 and 1 mole of O2, of SO2 and O2. But in this closed system, I'm going to put in 1 mole of SO2 and half a mole of O2. And that will make a difference. Yeah, it will make a difference. No, but then doesn't that make it hard to compare between 2 different reactions in terms of KC? Dad, you're absolutely right. So in reality, what are you trying to compare that? What are you trying to compare two different reactions? You wouldn't do that, would you? You'd compare the same reaction and how you've edited what goes into the closed system. In that case, you can compare those. We can compare these quite happily, Dan. But you're not going to compare this to another equilibrium. There's no point. What's the point? What are you trying to compare? Why do you want to compare it? You don't want to. You just want to compare equilibriums with themselves. Yeah? Okay. I don't want to get too lost in this, folks. Therefore, pressure, no. Catalyst, no. Yeah, no effect. Yeah. Volume, pressure, same thing. So I need you guys to realize this fact. It's really important. These are the true factors. Remember, now here's the trap. I'm going to explain the trap to you. This is something that I picked up, again, later in teaching. Question. Because let's make something clear. Question. Let's make something really clear first. Yeah? KC is a number that represents equilibrium position. We know this. Yeah? That's what it represents. Everyone in agreement? Yeah? So hang on a minute. So let's go for A plus B goes to C. Let's keep this simple. Sorry, dumb question, but why does pressure not affect KC? I'm coming to it, Ria. I'm coming to it. Right. Let's put them all as gases. Right. Okay. KC is a number that represents the position of equilibrium. Okay. So let's say that this has at 298 Kelvin, yeah, 100 kilopascals, yeah, that'll do. Standard temperature and pressure. Yeah. What I'm now going to do is I'm going to tell you that KC equals, let's say it equals 2.63. Okay. It's going to have units, products over reactants. It's going to be moles to the -1 dm to the +3. There we go. This is where I need to move this guy out the way because I feel like it's blurring my my point. Let's put it in a box. Love all my boxes. So, okay. First question. Right. So, question A. Let's make this like that. Let's do this. Okay. Ria raises temperature. Raises temp. ... Yield of C? Right. Ria, this is for you. So, Ria, you're going to raise the temperature. Can you run COFs for me and tell me what happens to the yield of C, please? Off you go, Ria. This is just for you. Go, go, go. Run me COFs in its entirety. I'll copy down what you say. Run COFs. It's actually COFSy. There you go, Ria. It's all yours. It's going to take her a little bit just to type it in, guys. Sorry that the lesson's gone on so long, but that's just part and parcel. Do. Adam, coffee or coffee? Because I need my morning fix. Hey, Adam, it's good to see you, dude. So this is one of my A2 lessons. It's interesting because you'll be able to do this, Adam. Oh, hang on a minute. Yeah, you can. It is GCSE, and I didn't teach you at GCSE, did I? So I love it. There it is. Knowledge. Forward reaction. Forward reaction is endo. Thank you very much, Ria. She's got the first mark. Oppose if you increase temp, RIA raise temp, increase temp, yeah, then therefore equilibrium will oppose change and reduce temp. Thank you, Ria. Equilibrium reduce temp. Next, keep going, Ria. Where's the favor? So forward reaction is favored to take in heat. Therefore, favor endo reaction. Yeah, I prefer, it is correct. Favor endo reaction. I'll give it to you. It is correct. You are correct, Ria. You just said it in a really weird factor. Favors forward reaction, favored to take in heat. I love that. So the forward reaction is favored to take in heat. Sure. Yeah, favored forward reaction. Next, shift. So position of equilibrium shifts to the right, increasing yield. Well done. Shift left to right, yield increase. Yield increases. So, Ria, as a result, let's look at what this does. So you've just said C increases. So what's going to happen to the value of Kc, Ria? Is it going to go up or down? Let's see if she can get it. In fact, anyone can post on the chat for this one, guys. Everyone contribute, please. What's Kc going to do? I love that Adam's put up. Love it. Well done, Adam. Adam, you haven't been here. I miss you too, sir. He's absolutely right, and so's Ria. Well done. Kc increases. Whoop, whoop. Well done, guys. Look at that. This makes sense. And the reason is, and we're fixing this in our minds, the reason is Kc is linked to products. More products, bigger Kc. So the question now is, and this is the trap they give you, and they walk you into it. Ria increases the pressure. Increases the pressure. ... Yield of C? Question mark? Yeah. Let's write down the equation again. A plus B goes to C, and they're all gases. Ria increases the pressure. Yield of C, please. I'm going to go for Nikita. Nikita, what's going to happen to the yield of C, please? Can you run coughs on it? Coughs, coughsy. I love a bit of coughsy in the morning, just like Adam does. Coughsy. Coffee, 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 coffee. I'm the world's fastest person at saying the word coffee. It's because I've had 14 cups of coffee this morning. As soon as I hit 20, I become the Flash, and then my lessons become gibberish at that point. But isn't the Kc dependent on how the increase in pressure? Yeah, no, it's not dat. I'm coming to it, dat. Come on. Let Nikita give the answer. Yeah. Come on, Nikita. Slow me down. Knowledge. 2 moles on left. 2 moles on left. 1 mole on right. Oppose. What did she do? Ria increased. Ria increased pressure. Therefore, equilibrium reduces pressure. Favor, it's going to reduce it. Favor side with less moles. Less moles. But isn't Kc only affected? Yes, Nikita, well done. Yes. Shift left to right. Yield increases. Yield increase. Kc. Oh my God, this is so important. Kc, unaffected. And the question is, WTF? What the food? Yeah, unaffected. Kc remains the same. And the question is, why? This makes no sense. Now, I'll explain why. The reason being is, if you were to graph, let's do Kc graphs. Yeah. So Kc graphs, yeah, if you were going to look at temperature and the value of Kc, and you were to look at pressure and Kc, here's what happens. So you expect, and by the way, I'm going to look at this. The great thing is we can say that Kc we'd expect for both of these for it to increase, which is awesome. So the Kc graphs for this would look like this. So for temperature, here's what the Kc value was before. Yeah. So this is low temp. Did I do that? Low temp or high temp? Yeah, low temp, high temp. Yeah, I'm just going to do a switcheroo. So at low temp, the value is like this. And then you suddenly increase the temperature and there's a jump. Kc increases and then it will level off. And there, so in this graph, what's happened? That there is when the equilibrium is being established. Equilibrium not yet reached. Yeah, it takes time for an equilibrium to be established. New equilibrium. Yeah, old equilibrium. Yeah, so we can see that the Kc has increased and has been fixed. Yeah, what happens to Kc in pressure? Now, the reason being is, okay, let's just go to Kc in pressure. Here's what happens. Kc at the original, right? This is low pressure, high pressure. I hope I've got that the right way around. What did we do? Do we increase pressure? Yeah. So here's what happened. It's amazing. There was a change, but it's not permanent. The reason being is Kc is a ratio of products to reactants. Well, here's what's happening. If you take an equilibrium, yeah, if you take an equilibrium with temperature, and what you're doing is if you take your balanced equilibrium with products and reactants, yeah, and it's already at equilibrium, what's going to happen is when you change the temperature, you shift it. You shift the balance. Now, what's going to happen is you want to hold it here. Yeah, you want to hold this new balance. In this case, you maintain the temperature. You see, this is the thing you see with temp. When you take a system which is at equilibrium with temperature, yeah, it's at a balance and it's held there. If you raise the temperature, you don't allow it to adjust. You just fix it at a new higher temperature. Here's the problem with pressure. With pressure, what happens is this. You had a balance of pressure and then you suddenly shifted it. You shifted the balance. But here's what now the equilibrium does is the equilibrium moves all the reactants over to a different side to reestablish the old equilibrium. Now, you can't do it. So what's going to happen is you can imagine that the pressure will increase, but then the pressure decreases. You actually see it in the value. If you're going to watch this, it's rather a cool thing. If you watched a pressure gauge, yeah, if you had a gauge that measured pressure in kilopascals, yeah, you had this gauge with your needle, yeah, and then it was like this. If you suddenly raise the pressure of an equilibrium, yeah, you raise the pressure of an equilibrium. Yeah. Well, what's going to happen now is the equilibrium now shifts. Yeah, the equilibrium shifts. Now shifts. And what's going to happen to the pressure? The pressure is going to get reduced. The pressure is reduced back down to what it started off as. Yeah. So it's returned to its previous status. Yeah. The products do increase. Yes. More product. Yep. You're absolutely right. There is more product, but the Kc value will return to normal as the ratio is readjusted. I know, it's bizarre, isn't it, Nikita? And that's actually where I'm realizing I've literally done a full lesson today. Holy moly, to the wire. I'm going to end today's lesson at this point. I will send you your homework, writing Kc expressions. Blimey, I'm really close to, I'm meant to be going into my next lesson. Holy moly. Right, let's go back to this. Guys, I'm going to end my lesson today there. I hope you found it entertaining. Applause in Italian. Okay, I'm being dumb, but why doesn't the same apply for temperature? Because we don't allow it to cool down, Ria. That's why. We raise the temperature, but then the temperature, we don't allow it to cool down. We just keep heating it up. You keep adding heat. You can't keep raising pressure. Imagine that. Take the pressure, raise it. Well, then they go, oh, it's going to get reduced. Let's just keep going. Well, hang on a minute. Your vessel's going to explode. You can't just keep raising it. Yeah, if you raise, you're shrinking the volume of your thing, you can't just keep doing it. Yeah, you get a limitation. So I'm going to end this webinar, guys, because my year 11s are now appearing and I need to go. Guys, I'll see you guys next lesson. I'll set you guys the homework for next, but I'll see you all soon. Ciao, guys. See you later.